it open. Awesome. Hey everybody, I'm really excited to be here at Nerd Night. In many ways, I consider myself a bit of a Renaissance nerd. I'm a man of many passions. But today I want to talk to you about one of my nerdities that's a bit unique to me. And that's my love of bubbles. For the last few years, I've had the pleasure of being one of the few people in the world that can actually say they work and play with bubbles for a living. This is part of what I do. And I really like it, so I want to get you to like bubbles just as much as me. And in particular, you can actually make bubbles explode with sound, which I find really fascinating. And I want to do this inside people in order to help them. So I think this is good. And without further ado, I want to introduce you to the incredible bubble. So I'm going to guess, a bar this size, most of you have probably seen a bubble in the past in some form or another. Maybe as a kid you blew bubbles, maybe as an adult. Maybe you do dishes and you have a sink full of suds. You like champagne, we call it bubbly. You prefer Guinness, like me, it's better with bubbles. No one likes flat beer, no one likes flat drinks. If you're the type of person to find yourself in a Spanish nightclub, maybe bubbles remind you of sweet rave parties. You know? Bubbles are everywhere. They're all over the world. And when you're someone like me, you think about bubbles. If you'll give me a minute, I think I got some lag with the remote, but I'm going to work through this. But I see bubbles everywhere, and I really like them. But the thing is, there's quite a bit more to bubbles than you probably realize. And if I could get some help from tech, awesome.
Doing good.
Thank you. I'm excited. There's quite a bit more to bubbles than you probably realize. The bubbles I showed you back there, they're all sort of created in the same way. There's a little bit of gas that goes into some sort of liquid or soap or something, and the bubble is born. But the bubbles I work with and the bubbles I really love, they've got a little bit more of an epic birth story. They tend to be ripped into the universe hard and fast out of nowhere and live fast and die hard. And to give you an idea of what I'm talking about, I don't know if anyone here likes popcorn like I do. If you've ever had a really stubborn bag of popcorn and you're pulling and you're pulling and you're pulling, and the damn thing just won't, open, and eventually it finally does and it just rips open everywhere, you got tons of energy released all at once. Alright, so that's ripping open popcorn. What you probably didn't know is you can actually rip open water in the same way. And when you rip open water or a liquid, you've got a hole in water. And what is a hole in water but a bubble? And these bubbles, like the popcorn, you get a lot of energy that's released from that, just burst all at once. And because of that, it gives the bubbles the power to destroy. And it's this sort of destructive power of bubbles that I hope to harness inside people for good things. And to give you an idea of when you might see this in normal life, maybe, most common cause of this, if you're ripping open water, you need something moving fast in it. And a propeller is a great example of this. If you look at this propeller, it's pretty torn up. And that's because it ripped open the water next to it and it created these bubbles, and the burst of energy from this tore this up. You want something with a little bit more gravitas? Yeah! Okay, so this is a conduit to the Hoover Dam. And if you see this giant crevasse, this is a 35 by 10 by 15 foot hole ripped in a 50-foot wide concrete pipe over a few days by bubbles. Give you an idea of the scale of this thing. This thing is a person. This is a hole made by bubbles. Bubbles got some force. And perhaps my absolute favorite example is the mantis shrimp. Yeah. So if you read the oatmeal, and if not, you should at least look this up. This is possibly the coolest animal on the planet. And one thing it can do is it can swing its arm with an acceleration over 10,000 times that of Earth's gravity, which is pretty fantastic, and it allows it to rip open the water next to it. And it uses this. It actually weaponizes bubbles. Shrimp can weaponize bubbles. And if it hits something with its arm moving that fast, of course it's going to do some damage. But this thing will attack shells or clams or crayfish. And the great thing is, even if it totally misses what it's trying to hit, if it swings next to it, the bubble it creates near it gives off enough energy to stun or kill fish. This would be like if you're in a bar fight and someone punches a foot left of your head and the wind off of their fist still knocked you out. The mantis shrimp is the Bruce Lee of the underwater world. I want you to watch this, just get an idea of what I'm talking about. Maybe. Yeah. Bam. This is at 2,000 frames per second. I'll show the end again. Maybe. All right. So, at 2,000 frames per second, yeah, back in business. All right, at 40,000 frames per second, you can really see what's going on, and that's this. All right, we're gonna go with it, and if there's time at the end, I'll show you, because it's pretty sweet. But the point is, this thing can move its arms fast enough to rip a hole in the water that emits a powerful shockwave. And this can kill and stun fish, even if it totally misses. So this is the sort of destructive power in bubbles that really fascinates me. And we're gonna keep going with this. But I want to use this in people. And why would I want to do that? Why would I want to make bubbles explode inside of a person? Well, you know, sometimes there are things inside of us that we don't actually want there. Tumors, poorly formed infant heart valves, or oversized prostates. There's material there that we just prefer to destroy, you know? And we can do that with bubbles. But in order to do it, we actually use ultrasound to make these bubbles inside people. So over the next several minutes, what I want to talk to you about is how are we going to use sound to start ripping explosive bubbles into people, and how can we use that to help people? This is the sort of problem I'm really interested in and I work on. So without further ado, we need to start with the first question, and that's, what is sound? Simple answer, sounds and vibrations. A lot of you probably knew that, but to give you an idea of what I'm talking about, next time you hum, say, or sing something, put your hand on your throat, and you'll feel something vibrate. And what exactly is going on there is you've got these string-like structures in your throat, sort of like guitar strings. They vibrate very quickly, and they run into air, and that runs into air, and that runs into air, and that runs into air. And this travels out. This is how sound moves. It's air running into air, running into air. Then it runs into your ear, and it hits these little hairs in your ear. And what is a vibration? But it's a push and a pull and a push and a pull. So it pushes and pulls against these little hairs in your ear. And when it does this, your brain says, hey, there's a vibration in my ear. I know what that is. That's sound. And remember, this description of sound is pushes and pulls, because I'll get back to it later, because it's important. But there's a bit more to it than that. You have different kinds of sound. When things are vibrating slowly, you have low-pitched sounds down here. And that's like a bass drum or a foghorn. And when things are vibrating more quickly, yeah, you have high-pitched sounds up here. And that's like a whistle or nails on a chalkboard. What can actually happen is, if you saw the little blue ball down there, things can vibrate so fast that we don't actually notice them vibrating. Our bodies and brains can't quite comprehend it for a lot of different reasons. And that's actually what ultrasound is. Now, the most common use of the term ultrasound, a lot of people hear that and they think, that's what we use to take pictures of babies. Oh, there we go. But you're right. Ultrasound is what we use to take pictures inside the body, particularly of infants. And this works the same way. We vibrate something up against mom. Mom's tissue runs into tissue, runs into tissue, and sound goes into mom. Sound hits baby, sound bounces back, and then all of a sudden, computers pick up that vibration on the surface of mom and say, I know what that is. And that's great. This use of ultrasound is pretty much the safest form of medical imaging we have. And it's just a wonderful experience. A lot of you may have been seen for the first time via ultrasound, or you may have seen your kids for the first time through ultrasound. But one of the things I really want to get across is ultrasound does a lot more than take pictures of babies. Yeah, I know, shock, right? We can use ultrasound to treat all sorts of different ailments. They've shown that you can increase the speed of wound healing by vibrating things with ultrasound, or clean teeth, or get drugs into the brain that's otherwise hard to reach for treating cancer, and doing all sorts of things with ultrasound. One of my favorite examples of this is the procedure called lithotripsy. And it's a big word for, we use ultrasound waves to vibrate a kidney stone to the point that it shakes apart. And this means that the kidney stone can be passed naturally by the body. Doctors don't have to go in with their scalpels and knives and cut it out. So it's much safer. There's way lower risk of infection because it's so non-invasive. And we can do a lot of great things with ultrasound inside the body. But we can actually break up more than just kidney stones. They already use this for these and blood clots. But it appears that some scientists have shown we can break apart just about any form of soft tissue. Fat, muscle, cartilage, tumor, all sorts of things. But in order to do it, one of the best ways is not just ultrasound, but with bubbles. Which is why for the last few years, I've been really interested in what exactly happens when you hit bubbles in the body with ultrasound. And this is the sort of thing that I look at. I'm really curious about like the physics behind this, and other people are using it to try to save lives. So it's good that we understand it when we do. And some of you might be wondering, why are there bubbles inside of me in the first place to hit with ultrasound? And earlier I talked about how you can rip a fluid or a liquid apart, and how ultrasound just pushes and pulls. Well, those pulls of ultrasound, those ultrasonic pulls can actually rip bubbles into people. Now the ultrasound you're using to get a picture of your baby, totally safe. You'd have to crank it up like 100 times beyond what that machine is capable of to rip a hole in your baby. So this is fine, yeah. So there's no need to worry, but I want to know what's going on here and how this is happening. So I like to think of it, the easiest way to think about this is you got to think of the bubbles kind of like springs. You know, you push on a spring, it shrinks down, it pushes back. You pull on a spring, it stretches out, it pulls back. Ultrasound. Ultrasound pushes on a bubble, the bubble collapses and shrinks down, but the bubble pushes back. Same thing. Ultrasound pulls on a bubble, the bubble grows and stretches out, but it pulls back. And just like if you bounce something up and down, the bubble keeps shrinking and growing and shrinking and growing. All right, fine, but it's not the sort of thing, at least it doesn't sound like the sort of thing that would destroy tissue. The reason this is actually so interesting is because it's a lot more violent than I'm making it look like here. When this happens, if a bubble could shrink and grow repeatedly without popping inside of you when it gets hit with an ultrasound, it could actually do it 400,000 times in the time it would take you to blink your eyes. That's millions of times a second. And because of this, the sides of that bubble, and whenever tissue or water is right next to that bubble, is moving really incredibly fast. And because of that, it's just got incredible stresses and pressures on it. And in addition to that, you've got all this gas inside the bubble. And you can think of the gas sort of like all the people in this bar. Yeah, it's a little crowded right now, it's a little warm, but now imagine all of these people were crammed into the bathroom upstairs, which is like a tenth of the size. So that's what happens in a bubble. It smashes down in millionths of a second to a tiny fraction of the size it was, but it's still got all that gas in there. So if you think it gets hot in this bar with a lot of people, in the inside of a bubble, when it gets smashed down by ultrasound, it can hit temperatures significantly hotter than those on the surface of the sun, thousands and thousands of degrees Kelvin, and pressures way, way higher than those at the bottom of the ocean. So you've got a lot going on there, and the bubble doesn't like that. That's not really a good state to be in. So it's smashed down, it's really hot, it's under a lot of pressure, and it just explodes to get rid of it. And when it does this, in addition to just exploding and hammering into whatever's next to the bubble, it also can emit powerful bursts of energy, shock waves, and it can even emit light in some cases. So these bubbles, they're not just shrinking and growing, they're violently collapsing and exploding over and over again, and it can break apart the tissue. Now again, I don't want you to worry, I'm not trying to create a weapon. What I'm showing, yeah, I know. But what I'm showing you is really not to scale. The bubbles that I look at are often a fraction of the size of a human hair. They're much smaller than the bubbles in champagne or soda or anything you're used to. So we're not like stabbing a pen through your kidney when we do this. We're just carving out a little tiny thing. And even though we're getting temperatures hotter than those on the surface of the sun, this is happening so fast that it doesn't have time to heat things up and cause much external damage. You only heat what's right next to that tiny little bubble. And now I want to show you something I think is really amazing. So this was a video done by Charlie Kane and the histotripsy group at the University of Michigan. This isn't my work, but they do some fantastic work and they let me use this. This around here, all this in the background is tissue. If you can see these dark spots, these are bubbles. And there's a strong ultrasound field. So watch what happens to these bubbles when we crank up that ultrasound. It's like taking a power drill to the tissue, except because you can focus those ultrasound at a specific point inside people, and you just make tons and tons of waves hit in one spot, it's like only drilling inside where you want to. I'll show you again, because, yeah. So this is the sort of thing I'm really interested in. How does this happen? How can we use this to help people out? And what are the fundamental physics of this? I don't do the medicine side, but there's a lot of things that we can't figure out from this. Because it's happening so fast, there's a lot that we can't get from even the world's fastest X-ray cameras. Which is where, and this is the level of precision that they can do it with. They were able to carve this M in. So this is something that could actually be used relatively safely. And I know there's a group that's actually starting human trials to shrink prostates with this. So it's got a lot of potential. But like I said, there's still a lot that we don't know yet. And that's where people like me and my lab come in. In a typical day, I'm sitting in my lab, I'm thinking, yeah, science. I'm thinking about my bubbles and I'm thinking about my tissue. And the way I tend to think about these things is often in terms of math. And we try to come up with equations that can roughly describe these bubbles exploding in people. But the math that comes out of this is really nasty, and I can't solve it. So with the help of my lab mates, particularly a buddy named Shahab, we write computer codes that do. And when they're done, they spit out pictures and videos like this of bubbles collapsing and exploding. And they give us estimations of what's going on with this sort of thing. And in the end, the final goal is insight. Can we figure out what's happening? So, this is my typical day, I'd say. But what I want you to take away from my Nerd Night talk today, bubbles are awesome. They do tons of things I bet you never knew about, and things that I don't have time to talk about tonight, but would be happy to if you engage me. Sounds are vibrations. They're pushes and pulls. And when you stick those pushes and pulls on bubbles inside people, you can make those bubbles collapse and explode violently. A brilliant show that can be used for a lot of good to help people, breaking apart all the things inside of them that we don't want. And that's about it. I hope you guys all really enjoyed my Nerd Night talk and you're as excited about bubbles as I am. And woo! I want to give a big thanks to my friends, lab mates, and my advisor who popped up to support me. So thanks to this table over here. You guys are awesome. Now, I would be happy to answer any questions, sounds, bubbles, or, whatever I got. So when I was applying to grad school, I was really interested in human injury, and they had a project on contrast-aided ultrasound, which injects little bubbles into the bloodstream to bounce sound off of them, and look at why that can cause hemorrhaging and why we don't do it in the U.S. We just sort of went from there. Yeah.
We got one over here.
Yeah.
How do you get, like that slide that showed the bubbles in the tissue, how do you get the bubbles inside of the tissue so you can target it?
So there's different ways, but some tissue's got bubbles already in it. Your lungs are full of air pockets, alveoli, and your intestines already have some in there. But things like that, I think that's liver tissue actually. That's actually because the ultrasound pressure waves, you're looking at things that are thousands of atmospheres, so the pressure is incredible, and the pressure is really strong pull, and it actually pulls apart that tissue. It's from atomic level fluctuations just running into each other, and they just want to run apart and rip apart.
So it actually creates the bubbles, and then you can apply more ultrasound to
Yeah, a lot of times those bubbles start from really, really tiny bubbles or other imperfections called nuclei. But yeah, that's in general it. Yes. On the left, and then the right, my left.
Actually, you first. All right, so we have a situation where we're internally drilling without invasion, and then we're coming up with loose material, loose tissue then. How does that get captured by the body and then expelled normally rather than go into some place and become contamination somewhere or dangerous?
Great question. So the way that this tears things apart is actually at a subcellular level, at an organelle level, is what I've been told, which destroys the cellular mechanisms for reproduction, which is great. But whenever you have damaged cells like this, you have little cleaner cells inside your body, sort of like street sweepers, called phagocytes, and they go around and they gobble things up like a vacuum cleaner, and then they get spit out in your body. If you ever get the chance, you should read Isaac Asimov's fantastic Voyage. He does a great scene on that.
Thanks.
Yeah. Or, you first, then you.
Yeah, okay. If your evil twin was doing the same research, what would he be excited about? Like, what kind of damage could he do? Because I'm a little scared right now.
Also a good question, and I'll admit, he'd be pretty disappointed. You have to get like someone to stand still right in front of you for a significant portion of time. It'd be much less effective than, I don't know, like a spork or something. He could destroy boats.
Yeah?
Yeah, or at least make them go slower. Yeah.
So my question was, you're just destroying cells and then relying on an immune response, which is essentially an inflammatory response to clean up the debris. How much of an issue is this in terms of the inflammatory response and associated damage to neighboring tissues?
So it's actually not very bad at all. I know that like the prostate studies that I've looked at and that people have like done this on, especially in mice and things, it is significantly faster healing than anything involving cutting it out with a scalpel or a laser, from what I know. Eric, if you got any thoughts on this, feel free to chime in.
I think that was all said.
Yeah, okay. Yeah, so it's pretty good.
When you're doing this, are you able to apply distance to you're doing the ultrasound, or how are you not putting stuff behind it or in front of it of what you want to sort of?
So these ultrasounds are actually done by arrays of thousands, or usually millions, because 1,000 by 24. Anyway, millions of little pressure transducers. So you're sending millions of really weak waves into someone, and it's only where they all smack together that you actually get something strong enough to create this problem, or this solution in this case. Yeah, it's coming from different angles, and it's only where they focus that you get this phenomenon. Yeah.
Is this something that is painful to the person, either during or immediately after, like, are you're asleep when it happens, and then how much does it hurt afterwards?
I don't know, but I would imagine significantly less than getting cut into. To the best of my knowledge, no more so than by any other procedure. Save maybe straight morphine. Yeah.
So you mentioned that the thing that causes the explosion is when the bubble collapses, the nitrogen gas inside of it.
Right.
But if you're creating the bubble in the first place with clear liquid, what gives you a vacuum?
So it's not a vacuum. You actually get vaporization of some of the water from this. And depending on what it actually comes out of, you can get like nitrogen in the blood, similar to the bends. So depending on where this is done, there is some gas or vapor in there. Yes.
What are the current limitations on how much energy
So it's really heavily dependent on the tissue. The softer the tissue, the better we can do it. So the brain, if you didn't have a skull, we could do this also. There's some French physicists working on getting around that problem too, from what I know, and they're doing all right. But it is kind of hard to focus energy in certain tissues, especially the harder ones or the ones that have just like a lot more going on. Like your liver's got this crazy network of veins, and you just want to be careful with that sort of thing. But apparently that's one of the places that can do it the best. But Those are some of them. Yeah. Yes. Yes, solar luminescence. It's still true that I don't completely understand it. If I had to guess, you've got a lot of heat and energy, so you're probably exciting some form of electron and it needs to jump down a state and emit a photon. Or you get a lot of energy crammed into an atom, and in order to decrease that, it gives off light. But I don't know the really in-depth mechanism of that.
Question.
Yeah.
So, if the bubble is collapsing and all that water and stuff, whatever, slams together, how high of pressure can we get?
So that's sort of debated. It's kind of hard to read that sort of thing. But there's a study at the University of Illinois, and you can look at the Wikipedia page on cavitation, the formation of cavities. But it suggests that they've seen pressures up to 10 to the 16th bar, which is like 10 to the 16th atmosphere, which seems unrealistic to me. Again, Wikipedia, but I know they said they've seen temperatures well up into like the thousands of Kelvin. I think things closer to like 10 to the 9th and 10 to the 12th are what I have personally seen in simulations.
I see a lot of promise.
I don't know. I know that they've encased people in bubbles, and I know that people have tried to encase a house at one point. But I don't know if it's many bubbles. That's a good question. I'll look into it. Yeah.
All right, thanks so much, Brandon. That was awesome. One more hand.